Ok. Oi, tudo bom? Bem-vindo à Louisiana. Nós estamos aqui em frente ao Rio Mississippi. Estou com Lane Simmons e também o Mike Manning. Nós somos do USGS, que fazem parte do LMG, que é focado na parte mais do Golfo do México. Nós estamos querendo ensinar e mais ou menos deixar esclarecido como que nós estamos pegando a água do Rio Mississippi. E agora eu vou deixar com o Mike.
Hello, thank you, and good morning. Today, as Monique said, we're in Louisiana, and welcome to the Mississippi River. Today we're going to be going out with Lane Simmons. This is one of his routine sites that he samples several times each year, and we're going to be using his samplers on the boat that they have in Baton Rouge and looking at his methods and how he approaches the work here at Baton Rouge on the Mississippi River. And so I'd like to introduce Lane Simmons.
Thank you. Good morning. So we're here at Baton Rouge. This site is funded by the United States Army Corps of Engineers, and they are a cooperator with us, so they have us come out here 18 times per year, and those 18 times are not necessarily distributed evenly. We try to catch specific events like peaks on the river, and the river's on a rise right now. So we're out here at a perfect time today. And today we'll be collecting a discharge measurement, which we will use to establish our 5 EDI, equal discharge increment, sampling points, which we will get bed samples, point samples, and depth integrated samples at all of these sites. We also have a gauge that's just upstream of here at Baton Rouge on the Mississippi River, and I will be visiting that gauge soon to make sure that the gauge height, the stage is reading correctly, because that's what our rating is based off of. The site has a stage discharge rating, and we also have some water quality parameters that our friend Paul Frederick operates on this gauge as well.
Our USGS office, located in Baton Rouge, Louisiana, uses multiple sediment samplers like the D96, D99 depth integrated samplers, the P6 200 point sampler, and the BM54 bed material sampler. Let's listen to Lane Simmons from our USGS office in Baton Rouge as he gives us a general overview of his sampling boat.
This is the boat that I use the most. It's the Spoonbill. This boat was built in 2016, and we tried something new with this boat. We wanted to be on the front doing the sampling rather than the back, and the reason why is because we sample a lot of bed samples. So we are purposefully sending a bed sampler to the bottom of the river and coming back up with material. And of course, that has a lot of inherent danger to it. You know, we could get the sampler caught, and that has happened before. So we wanted to be sampling off of the front. In case we get caught, the boat will behave more like it does if you had an anchor. So you don't anchor a boat off of the back, you anchor off of the front, because it's much easier to pull the anchor back out, and it's just a lot safer for the boat to be tied down from the front than it is the back. So that's why we built this boat. You see on the back of the boat here, we've got a generator. So this is just an air-cooled generator, and it powers a battery charger which sits inside the cab, and that battery charger charges a pair of deep cycle marine batteries in the bow of the boat. They're hooked together in series, and that's what powers our reel drive, and then the reel, and ultimately the samplers that go down to the bottom. So I'm going to step up on the boat now and show you a few things specifically. Okay, so here we are on the bow of the Spoonbill. This is the sampling boom that we use we turn this boom 90 degrees and we sample off of the starboard side of the boat. When we're sampling, this particular pole has the external heading sensor mounted to it, and then all of that gets mounted on top of the Doppler, which we swing 180 degrees so that it's hanging off of the port side of the boat. So we have bed sampler, BM54. It is the most lightweight sampler at 100 pounds that I have on the boat. So that's why I choose to put it on the starboard side of the boat, because I'm really looking to get counterweight so when when I have a sampler hanging over the side, I want my heaviest samplers that are not being used to be on the port side of the boat to act as a counterweight. And also acting as a counterweight is the generator in the back that I mentioned earlier. And then inside of the cab we have a spare reel, and we also have a spare reel drive system, because these are machines, and just like any other machine, it fails us every now and then, and we have to change out. So we try to have as many spares as we can, because like I said, the trip runs every other week, and it's a 5-day trip when we're out on the water, so we try to be as prepared as we can with backup equipment. So this sampler here is a D99. It's the heaviest sampler, and that's why I've chosen to try to put it kind of in the middle as much as I can. It weighs 300 pounds. It can sample 6 liters of water. Next to it is a point sampler, a P6200. It's a 200-pound variant of the modern point sampler that we use. And you can see it's operated electrically. So there's a conductor inside of this cable, and also the exterior of the cable serves as another conductor to complete the circuit, which powers the solenoid, which flips open the valve and allows us to collect the point samples. And we'll step into the cab. So of course our driver sits here, and he's got a GPS unit where he's able to mark the EDI waypoints, so the 5 equal discharge increment waypoints. As we collect those on the river, the driver will mark them on the GPS so that we can return to them later and actually make the samples. So I had mentioned that we had some spare equipment, so down here beneath this table is a spare reel drive and a spare e-reel. And over here is the battery charger, which is powered by the generator in the back, and it sends power to the batteries that are in the bow of the boat that power the reel drive system. And I think we can go back down now and we'll take a look at the back of the boat. So this boat is about 25 foot by about 8.5 foot. So it's a fairly big boat. It's got a good bit of weight on it. It's got twin 200 horsepower Honda motors on the back. And of course we need a trailer that's got brakes. So this trailer is equipped with surge brakes, since we're carrying around a hefty boat. And the reason why we're carrying a boat that's got this kind of power on the back, we really need that. If we're sticking this, when we stick this 300-pound weight over the side, especially as that thing starts making its way 70, 80, some cases 90, closer to 100 feet, and you're talking about velocities that can be 6 or 7 feet per second. It's a lot of drag on that sampler, and it's a lot of drag on the cable itself that's lowering the sampler to the depths in the river. So as the sampler gets lower, the driver usually has a sensation of, you feel that drag on the vessel. It starts to pull you back. So you really need that power. And we also use counter rotation. So this is a standard rotation clockwise, and this is a counter rotation counterclockwise. And what that does is it cancels out the torque from the motor, and it makes the boat behave more symmetrically as you're accelerating and as you're steering. We try to pin the boom down as best we can. So we'll put tension on here and have everything locked in place as best as possible, because the most damage that we see that happens to our sampling systems comes from the road. It doesn't come from out here on the river. It comes from having bumpy roads. So we try to lock everything down as best as possible when it's in motion on the highway. Power cable that's coming from my 2 deep cell batteries that are connected in series. A little port here that we can stick the cable through. forgot to get my handheld controller. So now I need to step over here and plug in. Like that, sorry. And I can see my voltage on there.
Our large river sampling boats are all configured differently as far as sampling rigs and various setups. We do not have a set blueprint of a standard sampling boat for large river work, although we are going more and more to the rear cab style of boat where the boat driver has a clear view of the work being performed on the front deck of the boat, and the samplers being deployed from the bow area as well. Let's look at our boat setups and how the reel drive system works with the main EF cable reel drive. This is one of the auto drive reel systems, and you get this as a kit without the brackets like this, but this is how we mount this on some of our booms. We use some sort of aluminum angle about this thickness, 1/4 inch thickness, and it fits on this groove. That would fit on the groove, and of course this would also be welded to a larger bracket that would then be fitted onto the boom. And the reel drive system comes with this holding bar and this secure nut that tightens down on this. And just for an example, like that, but it would be adjustable and be able to slide back and forth, because on this side there is a set of pulley wheels that 2 drive belts go on like this, and then it would subsequently fit onto the E reel or the B reel, one of the cable reel units, and be adjustable. So that's the way that works. And then on this side also there is a brake mechanism that you can tighten up or loosen. We have to do this on the heavier samplers to keep the sampler from slowly falling because of the weight. Then on this side there is the power hookup, and you are supplied with a power cable. It looks like this. It's got a positive and negative, and so this would plug into here like this, and then the other ends would go to a power source, DC battery, and then we have the controller box, and here it's loose, and this could be mounted in any configuration with another bar. This is a drive 2 unit. They came in a drive version 1 and 2, and now there's a 3. And so these are non-interchangeable with these different motors. And they're different settings here. The B reel or the E reel, normal would be operated with this controller, and then manual would be full speed all of the time. So we'll show you how this works and looks once we get out on the boat, and how we set our transit rate. Up and in and out would be the up and down of the reel, and so it's 2 different directions, and it's spring loaded. And then this rheostat on the end sets the transit rate, and this button would reset some of the settings. Our USGS office, located in Baton Rouge, Louisiana, uses multiple sediment samplers like the D96, D99 depth integrated samplers, the P6 200 point sampler, and the BM54 bed material sampler. Now Lane is going to explain how he applies the data from the ADCP measurement to point sampler operation.
So, and what we're going to do here, we're going to make one transect going from left bank to right bank. And when we get to the right bank side, I'll ask Al to hang out there for a few minutes, and I'll bring up QRev, and I'll plug that first transect into it to get my EDI waypoints. If I did not have an external heading sensor, I would want to make an additional transect going in the same direction to lay down my points, so that the GPS compass error, if you don't have an external heading sensor and you try to go in the opposite direction, it can skew the waypoints. We've even seen it try to put a waypoint on a bank, so it's very obvious in some places. In other places it's not so obvious, but the external heading sensor will allow me to use the reciprocal transect to lay down the EDI points. So that's what the plan is. So after we make the measurement, we'll have the EDI output from the QRev application, and I just use that table to enter the velocities into my spreadsheet when we get to each of the EDI stations. Sometimes I find that I have to adjust the velocities because there could be differences. It's a big system, and it takes us an hour or more sometimes to make the discharge measurement itself. So sometimes there will need to be a little bit of tweaking as you're staring at the boat velocity and the water velocity and Wind River. You may see some changes from what you got from the EDI. However, generally speaking, it's usually pretty solid. It's usually a really good estimate of velocity at that particular station. Sometimes we always don't return to the exact same point because we're using the discharge to mark our waypoints on our GPS. So we also have to pay attention to the depth. And we can have moving bed forms too, which is another reason that we have to pay attention to the depth. But that EDI output is a really excellent place to start when you're trying to determine your transit velocity and your nozzle size. Okay, so we're making our first transect for the day. We got to make at least two, and we can see our velocity contour here, and we can see boat speed and water speed there. And those are things that I'm paying attention to right now. And our boat driver Al is doing a fantastic job. He's keeping the boat speed below the water speed. We can go about the same speed as the water, but for the moment we got it smooth and steady, and everything is working fine. I can click there and make sure that my external heading sensor is communicating as well as the GPS, and that I am pinging and recording with the ADCP. I've got a screen back here which shows the three references, so our VTG, GGA, and then our bottom track. And you can see
we're almost there, bro. Anything else changed?
At the moment we are just now moving past center channel, and we're getting into the deep water, and we know that we have a moving bed because we did a moving bed test a few minutes ago. But as we look on this reference on the ship track here, we can see that the bottom track reference is starting to deviate from the VTG and the GGA, and that's because we have a moving bed here. And so as we go along and we keep getting in deeper and faster water, I'm expecting this this red line representing the bottom track to continue to deviate more and more from the GPS lock references. And when we're sampling, I will take this window and expand it so that our boat driver can see the vectors. So the blue are water velocity vectors, and the red line is the boat's path across the river, and then that red square is the current position, and that at the moment that's reference to whatever I tell Wind River I want the reference to be. So right now it's GGA. And we'll probably leave it at that because we have a moving bed. So I don't want my boat driver depending on bottom track to try to hold the boat still. We're wanting him to depend on a positional GPS reference. So I have imported the first transect into QRev. Today I know that I have a moving bed, but it's always just a good idea to go check for the moving bed in QRev before you compute the EDI points, because you need to make sure that you're using either GGA or VTG if you have a moving bed. If you compute the EDI points using BT and you have a moving bed, they're going to be wrong. So they're going to be skewed to one side. So we want to double check. So QRev says, yes, I have a moving bed, and then I'm going to force it to use the GPS and look again, and yes. So every way we know we have a moving bed. We can also tell that by looking at a path here. So you see the deviation of the red line as we got into the faster water. Clear signs we have a moving bed in every form. So we're using GGA, so we're good to go. Collect or go to determine our EDI points, and it's going to ask me to select a transect. In this case, there's only one to select. We can output the EDI format into a file, into a text file, and we can also have it pop up on the screen here. So now I've got my EDI table, and I want to document that right. So I'm going to open up an application called Snipping Tool, which allows me to take a screenshot. So we're just going to take a screenshot of the EDI table and the transect that was used to generate it. That way, when somebody comes back and checks our documentation, they'll have confidence that we use the correct measurement. So I'm copying that table and I'm going to paste it into a spreadsheet that I just use for general metadata. So now that is documented, and so you can see what all that else the spreadsheet has. Here's our efficiency. This is a spreadsheet that I wrote to help me decide transit rates and nozzle sizes. This is an air wet line correction that we can use if we have extreme angles due to velocities. And this is something that I use for my cooperator and my colleagues within the USGS, so that they can see what day we collected, how much discharge we had. Eventually this will be populated with a gauge height, and it's got the number of samples and the associated time with each sample that we'll be collecting today. So now we are ready to begin our second transect, and when we do so, I will have, let's see, I want to make this smaller. So I will have this screen up here, and I will be looking for these discharges. So there are two columns with discharge, and the reason why that is because QRev has to associate something with an ensemble. In order to get a position, that position has to be associated with an ensemble. So this actual Q is where QRev has to lock it in, but the target is what it's trying to hit. These are the actual 10, 30, 50, 70, 90% of total discharge, but QRev has to jump to the nearest ensemble to tie it in. So that's the reason why that's there. And there's such a small difference between them, particularly on these big rivers, like, you know, where we're working at today and what you guys will be working on, that these are just negligible. I mean, this is very small differences, but I just wanted to explain why there are two columns there. So while we are collecting the second transect, as Al drives across the river, I will be watching the total accumulation of discharge, and as we meet these thresholds for the 10, 30, 50, 70, and 90% of total discharge, I'll tell him to make a mark. And that's how we will establish our waypoints in the river for our sampling locations. As we can scroll, so we do the F12 to get that discharge summary, and then we can scroll over to Q divided by area. So this is an average foot per second velocity for the river. That number is 4.57, and I'm going to enter that into my point sampling spreadsheet here. 4.57, which takes in consideration for 3/16 nozzle, my target volume. So I have these liter jars, and the jar sits in the sampler at an orientation like this. So when the water gets to here, that's your overfill mark, because the water can start to touch the back of the O-ring, the bottle gasket that's in the sampler, and it can exchange material. So we don't want it touching there. So generally speaking, about 600 milliliters is the that's the maximum that we can put in here. So I want to give the lab at least 100 or so milliliters, so they'll have enough material to sample. So my target volume is 350 milliliters, which would fill it up to about right here. That gives me a little play on either side of that volume. So that's why I'm plugging this velocity into this spreadsheet, because it will let me know how long to keep the sampler open for. And we're going to keep the point sampler open the same duration for every sample. That way we can mathematically composite the sample and have more room to do statistics.
In the next videos, we will focus mainly on how we deploy the US P6200 sampler to collect suspended sediment samples at isolated depths. Our partners at the U.S. Corps of Engineers have used the discrete point data we collect for many years to model the Mississippi River's transport loads and energy at prescribed depths and across the channel's cross-section at various locations. Let's listen to Lane Simmons explain how this sampler works in more detail.
All right, so I'm assembling a point sampler head. So this is a P6200 or a US P6, the 200-pound variant. This is a solenoid that I'm threading into the head base, and it's got a channel that I can put these wires through. The wires are kind of fragile. I think they're like 22 gauge wires, so they're very small, and I've got this is just a gasket. You can, like a gasket that you would use an O-ring. I've just cut it and I've laid it in there, because if I don't, the wires have a tendency to jump out, and then when I clamp this piece on top, it crushes them. So that's what that is there for. And I've got to put what's called a plunger. So this is magnetic, and like I said, this is a solenoid. So when we apply power to the solenoid, it will push this plunger in and out, and that's what's going to operate this valve mechanism back here. So we can see, you can see the rod of that plunger as it goes through and hits the valve to open the valve. So I've got my solenoid and my plunger in there, and they're moving freely. So this head, it can't be put on the wrong way. It's, you can tell it's got the 3 pegs and then the cavity there to house the solenoid. So I'm going to flip it upside down, and I've got 4 stainless steel hex heads to hold it together. And we are currently developing a new point sampler that will have a similar head, except that it's 3D printed. The only metal pieces in the new sampler, it's going to be called a P21. The only metal pieces in there will be the solenoid and the plunger that opens the valve. The valve will be plastic, the head will be plastic, and it will be buoyant. If we drop the head in the water, it will float and we can go get it. The new sampler will also have depth integrating capabilities. So we can leave the valve open and we can use it just like a D99 or a D96. It'll have a smaller capacity than the D99 or a D96, but it will be able to sample in one direction because it has a valve. So we think we'll still be able to get about the same size sample, depth integrated, out of a P21. And we're hoping that that will be in production within a few years. Okay, so we have an assembled head for the P6200. Here. Okay, so I'm going to tidy up my tools in my box here. I keep all the parts for the P6200. And we can just leave it up here on the deck. And I'm going to put the head on the sampler. Okay, so we have the sampler body here, the 200-pound variant. It's got a notch in the side of the body with a hinge to go, and this is a hinge pin. Just work that down in there. And now the sampler is assembled. This is how we get to the conductors that go to the solenoid, and their power, or the main power, comes through this switch. So this switch is wired into the same batteries that power this motor, the 24 volt, the two 12 volt system, two 12 volt batteries hooked in series. So this will get that same 24 volt charge when I flip the switch, and that will be carried to a ground here and then a hot here. This wire has a wire inside of it with a plastic jacket. That's the hot wire that's inside, and then the external wrapping is the ground to complete the circuit. All right, got that. A little more. There we go. I'm going to connect the C connector to the hanger bar and put a hairpin through the clevis pin. Now we're going to test our electrical. Open it up here so that we can see the valve move, assuming that everything goes correctly. And I can hear it, so I know that's functional. Now we're going to lift her up and move her to the other side of the boat for sampling. So the point sampler, the P6200, it only has one size nozzle, and that's a 3/16. With the depth integrated samplers, we have options for nozzles. We have a 1/4 inch, we have a 5/16, and then we also have a 3/16. And that's one of the ways, combined with our transit rate, when we're taking depth integrated samples, that we can vary the volume. The way you vary the volume with this guy is by holding it open shorter or longer. So we're just going to stay in position. Our boat driver is going to hold us at the same spot in the river, and we're going to lower the sampler first to 90% of the total depth. Then we'll grab that sample, and then 70%, 50%, 30%, and 10%. And we're going to do that at all 5 EDI waypoints. And when we get to the furthest waypoint on the right, we're going to take 3 replicate samples, which puts us, so the 5 times 5, we do 5 points at 5 verticals. That gives us 25 samples, and we're going to take 3 replicates because that will give us more than 10% replicates. Okay, so as we saw earlier, I put the solenoid inside of the head. These are the leads coming out of the solenoid, and this is just like a trailer connection, just a 2-conductor trailer connection. I've used several different things. You can, I've got heat shrink in places. And of course, all those connections that's just another place where this thing can fail. And that is the most common failure, is that it doesn't receive proper voltage to the solenoid for the valve to open. So it can be kind of frustrating to troubleshoot, because you have to troubleshoot in a lot of different places. There's a lot of potential breaks in the signal chain. You know, first of all, you got your batteries, but you can kind of feel confident that they're working if the boom is working right, because it's powered from the same batteries. And then I have these switches that I build just out of an automotive switch. You just go to an automotive store and buy a switch like you would put in a car. And so this is one of my first places to troubleshoot. Not sure if you can see, but this particular switch has a light, an LED on the top of it. And I really like that, because when it's on, I can see the red light here. And if the red light is not on, then I know that that's a potential place. It could be the switch that is malfunctioned. And then from the switch, it goes to the reel here. So that would be the next place to test. And you would test this with a voltmeter. So I have a voltmeter that has the clamps on it that I can hang here, a voltmeter that you can read amperage with. So I just hang it on the cable, and I just touch the leads there, or I come over here and I take this apart if I'm having troubles, and I'll touch the leads inside of here to make sure that I'm getting the expected voltage, which should be fairly close to 24 volts. So far today, everything appears to be working okay. So at this time, I'm going to do a leak test. So there's no sample bottle in here. Actually, what I'm going to do first is I'm going to stick it beneath the water, and I'm going to let these surfaces get wet, because so on the back of this valve there's another surface that's like this, a spongy surface, and they really need to be wet to work properly. So the first thing we're going to do is just stick it under water, open the valve, and let all those surfaces get some water. Leak test now. I'm going to send it down to 9/10 of the total depth, so I'm headed down to about 40 feet. And I'm just going to let it sit there for about 15 or 20 seconds, bring it back up to see if it's got any water in it, without opening the valve. So it shouldn't have any water in it. This is what gives me confidence that that water's not getting in from depths that it's not supposed to be getting in at. Okay, and it's empty. So that's good news. Sampler is working as expected. So now I'm going to go down to my first sample depth, which is 43.2, and we're going to take a 14-second sample.
Timer on? Okay.
Ready? Go.
Yeah, tell him.
See?
Okay.
Good. 13. So we've got our point samples that we collected, and what we would expect to see is in the so we started on the left, at the left waypoint, and this was the first one that we collected, and we can see there's some really fine material in there. We kind of have a, that's the volume that we get. So what we would expect to see as we go across the river and we get into deeper, faster water, we would expect these volumes to go up, and we would expect the sediment concentration to increase. So we'll move to one from the center. So not much more volume, if any at all. There's a little bit. And the sediment looks a little heavier under there. And, okay, so this is from the center vertical here at Baton Rouge today. This was 10% depth, 30% of total depth, 50% of total depth, 70%, and 90%. So we generally would expect the volumes to get lower as we get deeper, and generally speaking, that's what happened. But you can see here at the 50% depth, we did get a little more volume. It's not unusual. It doesn't mean that it's wrong. It just things like that happen sometimes. Particularly if you have a wind that's blowing cross-stream or upstream. We do have a cross-stream wind today.
We also collect bed material from several sites along the Mississippi River. The sampler we utilize for that task is the US BM54, which weighs 100 pounds.
Okay, so this is a BM54 bed material sampler. It weighs 100 pounds. It has a spring-loaded mechanism inside. Right now it's cocked, and when it releases with a good bit of power, and it has a scoop that's like a semicircle that's going to come beneath here, just like a sediment shark. It's going to bite. So when it hits the bed, as it drops down there, the spring-loaded mechanism triggers, and the scoop shuts, and we should get a bed sample from it. So we've got a special Allen wrench to arm it again. So she's ready to send down to the bed. This is where you can get in trouble. When the bed sampler hits the bottom, this tension gets released, and sometimes that will allow it to jump off of the sheave and get bird nested, and that's bad news. So yeah, thank you, Al. So it's around 50 feet. So when I see 40 feet on the dial, I'm gonna have my hand up here ready to put tension on this cable so that we don't have it jump off of our sheave and our reel back.
Should I let go with the engines about that 40 feet?
I would say right now you can just go ahead and put it in neutral.
Okay.
And we'll just let it drop, and after I've reversed and I've started to come back up,
Catch up with the cable a little bit?
Yeah, right.
All right.
Okay.
Here we go.
Here we go.
You want me to do anything?
No, you're fine. Okay, so there's our bed sample from left.
Bed left.
And yep, we can double check our labels. That's always a good idea.
Yeah.
And we can move on to left center.
Okay, we got left. I'll get you left center ready.
So we're on location, and the depth is 57.
Roger that.
Just a recap of the topics we covered in these videos. We've gone over our sampling logistics and how we go about sampling our sites along the lower Mississippi River, and those locations and the offices which those crews are based. We've also talked about how we adhere to our large river safety protocols. We illustrated our ADCP mounts and our ADCP setup procedures in Wind River. We've explained our ADCP QA/QC processes and the software we use called Q Review. We've also discussed our samplers, how we select the proper sampler for the current river conditions. We've covered sampler support equipment like the bags, nozzles, and the materials they're made from. We've discussed how we go about establishing equal discharge sampling points across the river. We've shown how we monitor the sampler's position and the moving bed forms using live scope technology. We've demonstrated deploying the D96, the D99, the P6200, and the BM54 samplers. Thank you for watching our videos, how we engage in our large river efforts. We hope these presentations will support and improve your large river programs. Collecting data to monitor suspended sediment on large rivers is not an easy task. The USGS continuously strives to advance our methods and our samplers to expand our scientific understanding of these large river systems for future generations.